7.8 is exponential logarithmic functions. Most specifically, it's going to be exponential growth and decay. Okay, I'll drop this to you. Okay. I'm sure you'll get to this somewhere in biology at some point, but maybe not until the end of the year. So you'll have a head start on your classmates. As you're getting that situated, just know there's really not a ton of difference between the two formulas I'm about to show you. Okay.
What's the name of this?
It's on the picture that I just sent you. Okay, so we have two different equations here, but they're very similar, like I said. We have growth and we have decay. Notice the only difference between the two formulas is the negative power here in decay. Otherwise, the formulas are exactly the same. So growth means over time, the numbers are getting bigger, whatever it is we're measuring. And decay means over time, the numbers are getting smaller, whatever it is we're measuring. Okay? The only difference between the two formulas is the negative power versus a positive power. Let me try to define to you what all these different things mean. First off, E is not a variable. I know you look at this and you see it as a variable. It's not a variable. Remember that. Okay, there's that E to the X button above the natural log button next to the number 4 on your calculator. F of X or Y, you'll see it that way, is sort of our ending value, our ending amount, our ending quantity. A is our initial or beginning value, what we start with. K is this constant, okay, whether it's a growth constant or a decay constant, it just depends on which scenario we're looking at. And then T is time in years. Remember that, time has to be in years. So what's going to happen in these problems, you're going to be finding one of several things. The problem may ask you to find T, time. And you'll have to have everything else in order to do that. It may ask you to find the constant K. And then often when they ask you to find that constant, you're going to use it again in another problem because you're going to be looking for the time or the end value or their initial value. Okay? And then, of course, you have your initial value and your end value. So depending on the context of the problem, it's going to make you find one of those things. Okay? Very good. Constant does start with a C. In this formula, it's K. All right. Questions about the formula? We're going to go through 3 examples today. Okay? One of them we're going to find K first, and then later on we're going to use K. So I'll send this problem to you. We're going to work through this one together, give you an idea of what's going on here. So it's clear for you what it is we're trying to accomplish. All right. So here's this problem, exponential decay. So in this case, they tell us. We're using the decay formula. Okay. Talking about half-life of a radioactive substance. Now, you'll talk about half-life a lot in science class. Basically what half-life is, it's really simple. It's the amount of time it takes for some substance to reduce to half its value, for half of it to disappear. And how long does that take? Okay. Now in this particular problem, they're talking about carbon-14. And the half-life of carbon-14, according to this, is 5,730 years. So whatever particular amount of carbon-14 you have, it's going to take 5,730 years to reduce, to decay to half of the starting value. Okay? So what we're doing in this question is finding out the K, the constant, the decay constant. Okay? Now, it may seem like there's not a lot of information here, that the only thing they're giving us is this 5,730 years, which would be which variable in this formula?
Time.
Time, T, okay? They don't give us the starting value of how much carbon-14 we had or the ending value. The only thing that they tell us is that we know after 5,730 years, half of it's left. So for all intents and purposes, if we have A as my starting amount, after that 5,730 years, how much is left? 1/2 of A. Okay, that's the key thing here. So when we start by setting it up, the reality is if A is my starting amount, 0.5A or 1/2 A is what's left after 5,730 years. And what you're about to see is that that's good enough. I don't need more information than that. I don't need to know that there's, 7 million molecules, and then after 5,730 years, there's, 3.5 million. We don't need to know that, because what's going to end up happening is having an A on both sides of the equation is going to force it to cancel out. So that's what I've got. So if I plug in right here 0.5A for my ending amount, and A as my beginning amount, the A's are just going to cancel out on both sides, which is good, because now the only variable that's left is K. So here's what we've got. So when the A's cancel out, I'm just left with 0.5 equals e to the negative 5,730K. Now I switched it around because that's how we usually put the variable second, right? Now it's become a problem like what you've been working on in 7.7. How am I going to get that variable down? What do I have to do? You were just working on a worksheet. Yeah, take the natural log of both sides. Okay, so that's it. That's all you got to do. All right, take the natural log of both sides. So what happens to this negative 5,730K with the natural log next to the e like that? They basically just cancel out. Okay, and this power drops down. That's the way you want to think about this. Okay, and I told you guys this last week, but just as a refresher, this is really, you take this negative 5,730K, and then it's times natural log of e, which this is just 1. So for all intents and purposes, you can think of these two canceling out and this dropping down because of this. Okay. Now, how do I solve for K? What do I have to do? By? Okay, so do that. Finish this problem, please. Go 5 decimal places, because this number is going to be small. All right, because all I have to do is take the natural log of 1/2 divided by negative 5,730. 5 decimal places. A lot of your calculators are going to give it to you in scientific notation. So you have to know how to read your calculator. Okay, so if it says since you see e negative 4, that means whatever your decimal is times 10 to the negative 4th. So you have to convert that to a decimal, because I don't want to see any e's as answers. Plus, that's just not going to help you do this problem. So what you should have done for K is approximately 0.00012. How many got that? Good. Okay. Now, so that's this problem. I found K. Here's an example of where we're going to use K to find another variable. Okay, the next problem that I'm going to give you is still going to be about carbon-14. And the decay constant is the same. So we can use it now. Are there questions before we move on to that next part? Okay. I'll airdrop this to you as well. Okay. In this problem, we have a paleontologist examining the bones of a prehistoric animal. And this paleontologist estimates that these bones contain 2% as much carbon-14 as they would have when the animal was alive. So what they're saying is there's only 2% left of the carbon-14. So how much has been lost over time? What percent has been lost? 98%. Do we expect that the number of years compared to the half-life. Half-life is 5,730 years. Do we expect the number of years to be more or less than 5,730? Still carbon-14 we're talking about. More, because more of it's gone. Instead of just 50% being gone, 98% is gone. Okay, so we would expect this number to be significantly bigger than 5,730 years. Okay. Now, if we think about our formula again, okay, we know our K value. K is still that negative 0.0012. How long ago tells me which variable am I looking for? How long ago? Years or time. We're looking for time. So we're trying to solve for t. Okay, that's our goal. We're trying to solve for t. Now in this case, how much is left of A, whatever that starting amount is? 2%. So how do I write that? What is 2% of A? 0.02. So instead of having a half A, this time I have 0.02A. And the rest kind of follows just like the last problem we did, where we solved for K. In this case, we have to solve for T. So the A's cancel out again. And now I have an exponential equation with base E that you need to solve. So please do that. What's our strategy here? What are we going to do? Abe, what are we going to do here?
Do algebra.
What did we do on the last problem at this point? No. What do we do? What's the strategy now? Take the natural log of both sides. Take the natural log of both sides. Okay, go from there. All right. So again, this natural log and E basically cancel. This drops down. So I have the natural log of 0.02 divided or equals to negative 0.0012t. I can divide? Yes, now we can divide, Dave. So t equals approximately 32,600 years. Okay, so what we would say is this animal lived about 32,600 years ago, which is significantly more than 5,730 years, as we expected. Okay, the reason I talked about that is to establish some level of reasonability with our answer. Just remember, these problems have context. Your answers should stay in context. So yeah, you should write out a little thing saying what it was about. Did you divide by a negative? Because the natural log of 0.02 is negative, and then of course on the bottom you have negative 0.0012. That is also negative, so that gets to the positive. All right, let's look at another one. Questions before we look at the next one? Next one is going to be totally different context. It is going to be growth, yes. Okay, obviously this book's a little dated, and so this example's a little dated. Actually, you probably are the last group to use this book at our school. We're going to switch to a more current version of our book next year, I believe. The content will be essentially the same, but the stuff will be current, unlike this that happened before some of you were even born. Okay? Actually, 2007 to 2000. Some of you were not born yet. Some of you were barely born. But anyway, you'll get the point through this. Okay, here's what we got. We're examining the population of Georgia. Okay, in 2007, the population of Georgia was 9.36 million people, which, in case you were unaware, is 9,360,000 people. Okay, in 2000, it was 8.18 million, which would be that number. Now, you're going to see that so long as you're consistent, you could either write the number out or not. You can use 9.36 or 8.18 and 12 for our future problem, so long as your units are millions. if you're not comfortable with keeping the units as millions, you can write the whole number out. It's fine. It's up to you. Okay? Now, for part A, we're going to find K. So in order to find K, I have to have everything else. I have to have time. I have to have the starting amount. I have to have either the ending amount or a ratio of the ending amount like we did. We had 0.02 of that amount. We had half of that amount. In this case, okay, we do have a starting amount and an ending amount. Start with our regular formula. It's growth. So it's our same formula except instead of minus a power, it's positive. The power is positive, not negative. That's the difference, okay? So the first question is, do we have the ending amount? Yes. What is the ending amount? 9.36 million. Do I have my beginning amount? Yes. Which is how much? 8.18 million. Do I have the time? How long? 7 years, right? From 2000 to 2007. So I have everything I need except K. So it's just a matter of plugging it in. And then the problem ends up being the same thing. So in my case, I'm going to leave them as 9.36 and 8.18. My years are 7. Okay. What's my first move here? I need what? Yes, I got to get the E term by itself. So I have to divide the terms by 8.18. Now, I would leave it like that. I would not try to punch that in your calculator and see what kind of crappy decimal you get. Because eventually, well now, what's my, Abe, let's see. See if you paid attention. What's my move now?
The ln.
Of natural logarithms, what do I do with that?
You put it in the equation.
How many times?
Twice.
Twice. So I take the natural log of both sides. That's the phrase you're looking for. Take the natural log of both sides. Okay? Now, here's what I'm saying. Instead of converting this into some decimal, I can just take the natural log of the whole thing. And that's going to give me a more accurate number. A more exact number. Okay, we've been talking about this. What's going to happen on this right side? What am I going to be left with on this right side? 7K. Basically cancels out. Okay, so now all I have to do is divide by 7 and I'm done. And again, if you enter this in your calculator, okay, if you use your alpha y equals button to put a fraction in there, you can put all of this next to the natural log, or if you need to put them both in parentheses like that, do that. And then divide the whole thing by 7. Okay? And then you'll get your K. So go ahead and figure that out. Grayson, what do you got?
0.01925.
Very good. 0.01925. How many had that? Raise your hands. Good. So that's our K. Now, I can tell you that 99% of the time, once you find K, you're going to have to use it in the next problem, or the next part. Okay? Now, part B says, when will Georgia's population reach 12 million people? Which variable am I probably finding here? T. When. When means time. Okay? When means time. When is this going to happen? So what that means is I need to know what Y and A are. I need to know what K is, and then I'm good. Do I know what Y is? What's our ending amount? 12 million. What's our starting amount? 8.18 million. It's the same. And our K is right there. So we plug in. This is what we should be what we need to solve. So go ahead and solve that for T. And then when you finish, make sure you actually answer the question. And I will tell you round to the nearest year. Round to the nearest year for T. So, first move, divide by 8.18 again, and leave it like that. Okay, leave it like that. Because now I'm going to take the natural log of both sides. All right, so that basically cancels out. So I have the natural log of 12 over 8.18 equals 0.01925t. Just have to divide. We're good. What is T? T is like 19.907. So in how many years? In 20 years. So what year will it be? 2020. The starting year was 2000. So if we add 20 years to that, now I would accept a couple things. So Georgia's population reached 12 million by 2020. Now, if you said something like at the end of 2019, right, because it's not quite 20 years, it's almost 20 years, I would accept that too. But since I told you to round to the nearest year, it makes sense that you would have said by 2020. That's important in these kinds of problems. You have to figure out where you're starting. You got to figure out if you're answering the question. If you would have said, when will Georgia's population reach 12 million people, I don't think it makes sense to say in 20 years. Especially because of how outdated this question is. Here's why. In 20 years is 2041. Right? This problem is obviously very old. So to say in 2040, we don't know that. You can predict it. I think it makes more sense to say in 2020, knowing that we started this problem in the year 2000, which again, this just exemplifies the idea why we need a more current book. Right? But we still make the same point either way. I mean, we could look up what the population of Georgia was last year and see. Did you already look it up?
Yeah, I did.
How much was it?
10.8.
10.8. So I guess the thing is though, let's think about it. But let's think about it from if you're a city planner or city manager or business owner or something like that, or a home builder. Like would Georgia have been a good place to want to start building homes back in 2000? Yeah, I mean there's 2 million more people, over 2 million more people there. That's a good place to build homes. So using information like this is a prediction, right? It's not exact. Obviously it's not exact. But we can make the determination that if in 7 years we're seeing growth of over 1 million people, maybe in 14 years we can see that too. Or maybe in 10 years we can see that too, or in 20 years. It wouldn't be unreasonable to expect that kind of growth. And that's where something like this has a practical application that may not be something you'd think of. Okay?